Hey everyone, it's Mr. Glover here. So the topic today is on solving linear and quadratic inequalities. So it's going to be a little different than what we've done because up until this point, we've just been focusing on equations and functions in their entirety. The idea today is that there's going to be certain portions of the function that will satisfy the inequality, and those are going to be our answers. So rather than having the whole function or the whole graph as the answer, only part of it will be. So last chapter, we dealt with solving for a particular point of a quadratic equation. So for example, zeros in the vertex. So if we want to find the zeros of this equation, we could simply factor this function. So y 0 equals x squared plus x minus 6. And we can factor that. We need two numbers that add to 1 and multiply to minus 6. So we could go with x plus 3 and x minus 2. And so we have x-intercepts or zeros at x equals minus 3 and x equals positive 2. Okay, so that's the zeros. If we want to find our vertex, we could use completing the square, but maybe we'll use a different technique. So let's take our zeros and find the average. That'll give us the x coordinate of our vertex. So technically it's the axis of symmetry. It's going to be at the point minus 3 plus 2 all over 2, which is minus 1 over 2, or minus 1/2. So this is the x coordinate of our vertex. We can then plug this back into our function, and we can find the y coordinate. So y equals negative 1/2 squared plus 1/2 minus 6, which is going to give us, just hold on a second here. It's going to give us negative 5.25. So our vertex will be at the point negative 1/2. And actually, let's just keep it in decimals. That will make it a little easier. Negative 0.5 and negative 5.25. All right. So we've done this so far, and what we're doing is we're finding specific points. So let's now open up our answers to a range of values. So instead of solving for a specific point, what if we solve for a range of points? We call this solving an inequality. For example, let's say that we had a function that looks like this, but maybe we're only interested in the points where y is greater than 0. Maybe we're only interested in these points. That's where we're going with this. That's this idea with inequalities. So inequalities that we're going to be dealing with in this chapter have to do with either linear or quadratic functions. So we're going to call them linear inequalities. Or we're going to call them quadratic inequalities. And we have four basic types of inequality. We could either have greater than, so something like this. We could have greater than or equal to. We could have less than. Or we could have less than or equal to. Okay, and we've just got to be careful that if there's this equal sign below, that includes a specific point. If the equal sign is not below, then it's everything greater than or everything lower than a specific point. Instead of dealing with every y value, these functions only allow certain y values, specifically those less than or greater than 0. Okay. So let's say that we had an inequality, something like 2x plus 1 is going to be greater than 0. If we want to figure out what values satisfy that, we're going to have to figure out which y values or which x values are associated with a y value of 0. We're going to get a graph. It'll look something like this. And what we're interested in are all the points above 0. We're interested in this part of our function. The bottom part we don't really care about because it's less than 0, so we can almost cross that off. We want to know what x values are there from this point onwards. That's essentially what we're going to be doing here. So let's try some questions. Graph the following inequality. 3x minus 4 is greater than or equal to 0. Then draw the possible x values on a number line. Okay, so 3x minus 4 is greater than or equal to 0. Technically, we can probably graph this, but we're going to do it on a graphing calculator or on Desmos so that we are a little more exact. What we want to do, step 1, is we're going to graph the function y equals 3x minus 4 and find its x-intercept. So we're going to graph the function. Step 2, we're going to find the point where y equals 0. Okay, once we know that point, we can then figure out our x values. So then step 3 is going to be find the x values where y is greater than or equal to 0. So we're going to have to switch to Desmos to get started on this, and we're going to have to graph our function. So we're interested in 3x minus 4. So going over to Desmos, y equals 3x minus 4. So we've got this as our function. And we can zoom out or we can zoom in, but we're not really interested in that. What we're interested in is finding the point where it's greater than or equal to 0, or finding the range of values. Okay, so I'm going to go to where it is 0. It's right here. Everything to the right of this point, so if I trace up, the graph, all of these values will give us a y value that's greater than 0. So anything above this line works for us. Okay. This is the point that is the first point where we're equal to 0, and anything to the left of this, anything below this point, we have y values lower than 0. So essentially, the idea I'm trying to convey is that as you get y values that are greater than 0, your x values go up, and the lowest x value that satisfies our needs are 1.33. So anything above 1.33, we've got a y value that works. Anything below, we don't. So we can go back to our question. We can draw a sketch of it. It's going to look something like this. We'll have a y-intercept of minus 4. 1.33 was about our x value. And so we're going to get a function that looks like this. We're interested in the portion where we're above 0. So we're interested in this portion. That's our answer set. And so x equals, or I should say at x equals 1.33, y equals 0. So x is greater than or equal to 1.33 is our answer. If we want to draw this on a number line, zeros in the middle, we'll make this point 1.33. And essentially our answer is going to be a line above this. So it's going to be the line from here over to the right. Note the x-intercept of the equation y equals 3x minus 4 is x equals 1.33. Since this point marks the start of our solution set, we have a special name for it. It's called the critical point or the critical value. And this is important, so this is something I'm going to highlight. Since this point marks the start of our solution set, we call this point the critical value. Sometimes the critical value is included if you've got greater than or equal to or less than or equal to as your inequality. If you have exclusively greater than or less than, the critical value won't be part of your solution, but it's anything above that point. The critical points are included in our system. We write them as open points, or sorry, closed points. If they're not included in our system, then we leave them as open points. So for example, what we just drew with a closed dot, that indicates that the solution is including 1.33. If we had drawn it like this with an open dot, that would indicate that we don't have 1.33 in our solution set. All right, so graph the following inequality: x squared minus 2x minus 3 is less than 0. Draw the possible x values on the number line. So this is the same kind of question, except there's a couple of key differences. The function itself is quadratic, not linear, and we're looking for less than 0, not less than or equal to 0. So let's go ahead and let's graph this. X squared minus 2x minus 3. Go over to Desmos. X squared minus 2x minus 3. We get a function that looks like this. All right, so we've got two portions of the graph, if you will. We've got the portion below 0. We've got the portion above 0. And the question that we're trying to answer is asking us for less than 0, exclusively less than 0. Okay, and so we can go back to our graph. Oops. We can look at our critical values, our critical points. There's minus 1, which is a critical point, and 3, which is a critical point. We're also going to have a vertex at 1 and minus 4. So we can now go back and we can graph this. We've got an x-intercept at minus 1. Whoops. We have an x-intercept at 3. And I believe this was our vertex. So our function looks something like this. This is going to be the point x equals minus 1. This is going to be the point x equals positive 3. And I believe those are the numbers. I'm just going to double check. Yeah. So what we're interested in is everything where this function is below 0. So we're interested in this bottom part. We're interested down here. All right. Now, if we had less than or equal to, we would include minus 1 and 3. Since we aren't, then technically the answer is going to be x is strictly less than 3 and x is strictly greater than minus 1. If we want to represent this on a number line, we draw the number line, put 0 in the middle. We've got minus 1 over here. We've got 3 over here. And I'm just going to draw my ends of my line with open circles, and that tells me that those points are not included in the answer. So that number line is the solution to this inequality. Or we could represent it using an inequality like this. Either of these are answers. The right-hand side of the inequality doesn't always have to equal 0, though. If a non-zero term exists on both sides of our equation, we can solve the problem in two different ways. One way of doing it is to move everything to one side of our inequality and solve as before. The other way of doing it is to plot each side as a separate function and find the intersection rather than the x-intercept, okay? So we've got options. I'm going to give you a word of advice, though, or caution. If you are going to divide by a negative number, then you're going to flip the inequality, or you're going to reverse the inequality. So an example of this would be if you had something like minus 3x is greater than 2. If you divide by minus 3, x now becomes less than minus 2/3. So because we divided by the negative, we had to flip the inequality around. It's probably not going to come up a lot, but it is something to be aware of. All right, so let's try one of these questions. Solve the following linear inequality. 1/2 x minus 1 is less than or equal to minus x plus 5. What we're going to do this time is we're going to solve this equation by graphing two functions and finding the intersect. And then the next question, we'll go ahead and we will actually solve it by rearranging. So what I'm going to do is I'm going to graph the first part of our function, 1/2 x minus 1. I'm going to graph that as one function. I'll call it y1. I'm going to graph the other half of my function, minus x plus 5, as a separate function. I'll call it y2. And I'm calling it that because in a graphing calculator, you input your functions as y1, y2, y3. In Desmos, I'm just going to define two different functions. What I'm going to do, step one, is I'm going to graph both, y1 and y2. Step two, I'm going to find the critical value, which is the intersection. And then step three, what I'm going to do is I'm going to find the x values that satisfy the inequality. Find the x values that satisfy our inequality. All right, so we've got a couple functions to graph. We've got 1/2 x minus 1 and minus x plus 5. So let's graph these. 1/2 x minus 1. Y equals 1/2 x minus 1. There's our first function. Our second function was minus x plus 5. So now we've got two functions, okay? So we can tell where they intersect each other, the critical value is 4 and 1, okay? And now this is why this technique is a little bit trickier. You've got to kind of make sense of what you're being asked, all right? So going back to our question, 1/2 x minus 1 has to be less than or equal to minus x plus 5. So what that means is this first function, this red function, has to be less than or equal to the purple function. So we've got two kind of portions to our graph, if you will. Over here, to the left of the critical value, the red function is lower than the purple function. In other words, this function is less than or equal to this function. On the right of our critical value, now the red function is greater than our purple function. All right, so what we've got to do is we've got to only include x values that lead up to and including the critical value. Anything past that point doesn't satisfy the inequality. So if you have a critical value or a critical point at 4 and 1, we can say intersect at the point 4 and 1. This tells me that the critical value is x equals 4. The question now becomes, is it including or not including 4? It looks like it is. So that means x is less than or equal to 4 is our answer. Because if you go back to our graph, any x value that's below 4 creates or makes this function less than the other function. That's what we're trying to do. So we go back to here. We want to answer this on a number line. So we draw the number line. Put 0 in the middle. We put 4 over here. So our answer is going to include 4 because it's less than and equal to. And our number line looks like this. We can test our solutions by substituting one or more values into our inequality. So let's pick an x value that's less than 4. Let's plug it into our function and let's test to see if what we did actually works. All right. We're using the inequality 1/2 x minus 1 is less than or equal to minus x plus 5. Okay, so less than 4, well, let's use 2. We're going to try x equals 2, and that's because 2 is less than 4. So if we plug 2 in, 1/2 of 2 minus 1 is less than or equal to minus 2 plus 5. 1/2 of 2 is 1, so this is 1 minus 1. The right-hand side will become minus 2 plus 5. Or we'll be left with 0 is less than or equal to 3, and that's true. So this point, x equals 2, works. If you're not convinced, you can pick another point. Try like minus 7. Anything lower than 4 technically should work, and 4 itself should work. All right, we're going to try another one of these. This time, though, we're going to do it the other way, where we just rearrange everything to one side. You might find this is easier. You might find this is not easier. It's going to be completely dependent on how you like to solve these functions or these problems. So we start with our equation, 5x. Maybe I'll write the steps. So step 1, we're going to rearrange the equation. So everything is on one side. So we had the point 5x is greater than 2 times x squared minus 6. We can expand these out, I suppose, to 5x is greater than 2x squared minus 12. And then we're going to move 5x to the other side. We're allowed to subtract it, and we won't change our inequality. It's only multiplying and dividing by negatives. So 0 is greater than 2x squared minus 12 minus 5x, and the mathematician in me hates that it's written this way, so I'm going to write it as 2x squared minus 5x minus 12. Doesn't matter if you do this, and quite honestly, you don't even have to expand your brackets. Now we've got some functions to work with. So step 2, we're going to plot y equals 2x squared minus 5x minus 12. And then step 3, we're going to find the critical value. That's going to be the point where y equals 0. Okay. Once we've done that, last thing we've got to do is just find our x values, find the solution. So step 4, use the critical value to find a solution. So step 1, we've done. Step 2, we've got to go and do, we need to plot 2x squared minus 5x minus 12. So go over Desmos, 2x squared minus 5x minus 12 is our function. All right, now it looks like this. What we are interested in is going to be the part, is it below or greater than 0? Where this function is less than 0. And remember, the shorter side or the narrower side is going to be the lower side. I always thought of this as, I know that they often teach this like the alligator eats the bigger thing. I always thought of it as a distance problem. So like these two are separated more, so that must be a bigger side. This is a narrower point, so this must be a smaller side. So we're looking for things that are less than 0. Okay. So we're going to go back to our function. We're going to find our critical points, and the critical points are negative 1.5 and 4. So the question now becomes, am I looking at the points between these? Because the points between these give me y values that are negative. Or am I looking at the points outside of these? Because these are going to give us y values that are positive. Since I want the points where y is less than 0, I'm only interested in this part right here. And you know what? You can actually define this in Desmos with squiggle brackets. You can go y is less than 0. And if you've actually bothered to define it with y, it'll only graph that part of the function. So this is the answer. This is like our set of solutions. 1.5 or minus 1.5 is one critical value. 4 is the other. And since we're talking exclusively less than, we can't include them. So minus 1.5 and 4. Go back to here. find the critical values, x equals minus 1.5 and x equals 4. So if we want to find a solution, well, we've got two ways of interpreting this. We can say that x must be exclusively less than 4 and exclusively bigger than minus 1.5. If we wanted to answer it on a number line, though, draw the number line, put 0 in the middle, 4 is over here, and I guess we should kind of try to draw it to scale. So minus 1.5 is right here. We're interested in the points between these, so that is our solution. All right, we're almost done. The length of the rectangle is 2 centimeters greater than its width. The area of the rectangle is at least 20 centimeters squared. What are the possible dimensions of the rectangle in terms of to the nearest millimeter? All right, so we've got to kind of set this problem up to start. We've got to draw a diagram and we've got to kind of interpret what we're doing here. So we've got a rectangle. There's going to be a length and a width dimension. Okay, we'll call this the length and we'll call this the width. Now, the length of a rectangle is 2 centimeters greater than the width. So what I'm going to do is I'm going to just call the width x. I don't know what the width is. Then I can define length in terms of x. And since the length is 2 greater than the width, I can just call it x plus 2. Right? Now I've got both dimensions of my rectangle written in terms of one variable, some unknown variable, we'll call it x. All right, so now what I know is that the area is at least 20 centimeters squared. And you know what, let's change this to centimeters. At least 20 centimeters squared means that my area is greater than or equal to 20. Okay. So if my area is greater than or equal to 20, that means length times width is greater than or equal to 20. And now I need to replace length and width with terms that involve x. So I'm going to replace length with x plus 2, and I'm going to replace width with just x. Okay, we're almost done. We now have to multiply these brackets. So x plus 2 times x is x squared plus 2x. And that's greater than or equal to 20. And now we've got options. Do you want to graph it as 2 functions? Do you want to graph it as 1? I think at this point, people will find it a little bit less confusing if we just graph one function and find our x-intercept. So we'll do that. But you can do the 2-function technique if you want. We're going to move the 20 to the other side. So x squared plus 2x minus 20 is greater than or equal to 0. We're going to plot this function, and we're going to find out where it's greater than or equal to 0. So x squared plus 2x minus 20 is what we're interested in. All right, so x squared plus 2x minus 20, we'll define it as y equals. Okay, this is what the function looks like. We've got critical values at 3.58 and negative 5.58. All right, we've got a minimum down here. We don't really care about the minimum. And we're interested in being greater than or equal to 20. So we're interested in points where our function is exclusively greater than 0. So over here or over here. All right, so if we go back and we want to graph this, let's go back, draw a quick sketch so we don't have to constantly bounce back and forth between these two. We've got a graph that looks something like this. Oh, I think it doesn't really matter for now whether the vertex is on the right or left of 0. We've got a point here and a point here. This is the point x equals negative 5.6. This equals the point that x equals 3.6. All right, and now the question is, are we interested in the points between these values or the points outside of these values? Well, the question's saying we want the points greater than 0, so we only want the y values that are up here. So we're actually only interested in x values that are either lower than this or greater than this. Okay. But now this is the tricky part here. We have to remember what we're doing and why we're doing it. We are talking about dimensions of a box. Okay. If we have a width that's 0 or less, then we don't have a box. It doesn't actually exist. So while technically part of our solution set could be over here, we're not actually going to include those answers because we can't have negative width of a box. So anything over here, we're going to kind of disregard this. And the reason why is that we can't have a negative width. So really, this is our answer over here. This is our solution. Everything above this point. Okay, so our solution set is that x is greater than or equal to 3.6. It's greater than or equal to because we want greater than or equal to 0. We could draw it on a number line if we want to. I don't know if the question really asks us to, but it's not a bad idea. So we have a solution set that looks like this. And last but not least, we could always check to make sure that it works. We could always pick a point. So let's just pick test x equals 4. We want the length times the width to be greater than 20. The length is x plus 2, so 4 plus 2 is 6. The width is x, so 4. 6 times 4 is 24, which is greater than or equal to 20, so this works. So we could say length equals 6 and width equals 4 are possible solutions. All right, so that is where I think I'm going to stop things here. We've gone over quite a bit of new material. It's kind of strange and it's going to seem kind of weird because we haven't thought about functions in this way yet. We've been specifically looking at 1 point or 2 points, the y-intercepts, the x-intercepts. Now we're actually applying some context. And so we have to really, really think about what we're doing and why we're doing it. So I've got a few questions for you to try. It's page 355 in your workbook. 1 and 3 to 8 is what I want you to try. If you feel like trying some of the higher up questions, they're mainly going to be word problems, and they would be a good test of whether this stuff is making sense or not. This is all I want from you for today. All right. So I'll end the chat now. Hopefully everybody has a great rest of the day, and I will see you all. I'll see you all tomorrow. Bye for now.